When we hear the word radiation, what kinds of images come to mind? Probably things like mutations, nuclear explosions, or cancer-frightening and dangerous ideas. But is that really the full picture? Of course, it's true that high levels of radiation exposure can be harmful, but not all radiation is dangerous, and it certainly isn't always harmful. In this video, we'll take a closer look at how radiation is created and clear up some common misconceptions. In the last video, we briefly touched on what radiation is. The key takeaway from that was this: radiation is energy released from atoms. Now, let's dive a bit deeper. We'll explore the types of radiation and their characteristics. Have you ever sat around a campfire or fireplace and felt the warmth on your skin? That's thermal energy reaching you from the fire. Radiation works in a similar way. It's a flow of energy. The difference lies in the type and amount of energy being transmitted. To define it more precisely, radiation is the flow of particles or waves emitted when radioactive materials decay. Based on the nature of this flow, radiation can be classified into two major types: particle radiation and electromagnetic radiation. Let's start with electromagnetic radiation. If you've read a science book, you've probably seen a diagram like this: the electromagnetic spectrum. This shows the range of electromagnetic waves, organized by wavelength and frequency. Somewhere in the middle of this spectrum is visible light, the light we can see with our eyes. To the left, there are radio waves and microwaves, which are used in broadcasting and in your microwave oven. On the right, there's ultraviolet light, the stuff we try to avoid in the summer, and then, finally, X-rays and gamma rays. X-rays are used in medical imaging, like chest scans. Gamma rays are more familiar to most of us from sci-fi movies and superhero stories. But both are real types of radiation, and both are just high-energy electromagnetic waves. Because they have shorter wavelengths, X-rays and gamma rays carry more energy. If we think about the energy equation, shorter wavelengths mean more energy. Now, what about particle radiation? This type includes things like alpha and beta particles, which are emitted from the nucleus of an atom during radioactive decay. These types of radiation come from the decay of unstable atomic nuclei. Let's take a moment to summarize. Radiation can be divided into two main types: particle radiation and electromagnetic radiation. Electromagnetic radiation includes X-rays and gamma rays. Particle radiation includes alpha and beta particles. Got it so far? We've said radiation is a flow of energy. So why does this energy get released? To answer that, let's go back to the atom. There's a principle in science. Everything in nature tends to move from unstable to stable. Atoms are no exception. Their nuclei always seek a more stable state. But nothing comes for free. To become stable, the nucleus must release energy. That process is called decay. The first type is alpha decay. This happens in heavy, unstable nuclei with atomic numbers above 74. They release a helium nucleus, 2 protons, and 2 neutrons. When this happens, the atom loses 2 protons. So its atomic number decreases by 2. For example, uranium-238 atomic number 92 undergoes alpha decay. It emits an alpha particle and becomes thorium atomic number 90. That alpha particle is what we call alpha radiation. The second type is beta decay. A nucleus is stable when it has the right balance of protons and neutrons. Too many or too few neutrons makes it unstable. We classify these as either neutron-rich or proton-rich nuclei. In neutron-rich nuclei, a neutron turns into a proton. This emits a beta minus beta particle, an electron. In proton-rich nuclei, a proton becomes a neutron. This emits a beta plus particle, a positron. The purpose is to restore balance between neutrons and protons. This is what we call beta decay. In beta minus decay, the atomic number increases by 1. In beta plus decay, the atomic number decreases by 1. Don't worry if this feels complex. Here's the key point. Unstable atoms decay to become stable, and in doing so, they release alpha or beta particles. Now, what about X-rays and gamma rays? These are electromagnetic waves, not particles. Let's start with gamma rays. Atomic nuclei have different energy levels. You can think of them as steps or layers of energy. The lowest level is called the ground state. The higher levels are called excited states. Here's a way to picture it. Think of a person who's angry and agitated. They're unstable and unpredictable, but once they release that emotion, they calm down. Nuclei behave in a similar way. When a nucleus is in an excited state, it releases energy and returns to its ground state. The energy released is very short in wavelength. It falls in the gamma ray region of the electromagnetic spectrum. So, we call this energy a gamma ray. They are waves, not particles. Because only energy is released, the atom's identity doesn't change. Now let's talk about X-rays, which are more familiar to most people. There are two ways X-rays can be produced: characteristic X-rays and Bremsstrahlung X-rays. Characteristic X-rays are produced in two main ways. First, when energy is released inside the atom, it can knock out an electron from its orbital. This leaves an empty spot in the electron shell. Second, an incoming high-speed electron can also hit and eject an orbital electron. Either way, a vacancy is created in the inner shell. Each electron shell has a specific energy level. So, when an outer electron fills the vacancy, it must release or absorb energy to do so. When an outer electron moves in to fill the empty spot, it releases energy equal to the difference between the two energy levels. This energy is emitted as an electromagnetic wave, and because it falls within the X-ray region, we call it an X-ray, more specifically, a characteristic X-ray. Bremsstrahlung X-rays are easier to understand with an analogy. Think of how a meteor falls to Earth. As it passes near Earth, gravity pulls it in, slowing it down and causing it to release energy. Something similar happens with fast-moving electrons. When a high-speed electron passes near a nucleus, the positively charged nucleus pulls on the negatively charged electron. This force bends the electron's path and slows it down. The lost kinetic energy is released as radiation. This emitted energy is called a Bremsstrahlung X-ray. This is the principle behind X-ray machines used in hospitals. So far, we've talked about particle radiation and electromagnetic radiation. Let's wrap up with a quick summary. Radiation comes in two main types: particle radiation and electromagnetic radiation. Particle radiation includes alpha and beta particles. Alpha particles are released during alpha decay, when a helium nucleus is ejected from the atom. Beta particles are released during beta decay, when the ratio of neutrons to protons becomes unbalanced. This produces either beta minus or beta plus radiation. Electromagnetic radiation, it includes gamma rays and X-rays. Gamma rays are wave energy released from unstable nuclei as they move to a more stable state. X-rays are produced in two ways. One is characteristic X-rays, created when an electron fills a vacancy in an inner shell. The other is Bremsstrahlung X-rays, produced when a fast-moving electron is slowed by a nucleus, releasing its lost kinetic energy as radiation. In particle radiation, the number of protons changes, so the atom becomes a different element. But in electromagnetic radiation, only energy is released. The element stays the same. Through these different mechanisms, unstable atoms transform into stable ones by emitting energy. This entire process is mapped in what's called a radioactive decay chart. For example, cesium-137 undergoes beta- decay and becomes barium-137 mem about 94.6% of the time. This decay releases a beta particle with 0.512 MeV of energy. Then, barium-137 mem releases a gamma ray and becomes stable barium-137. Yes, this can all feel complicated. But here's the simple message I want to leave you with. Radiation is energy released as atoms become stable. Different atoms emit different types and amounts of radiation. So here's what I really want to emphasize. Not all radiation is dangerous. Each radioactive element has its own energy level and behavior. Just because you're exposed to radiation doesn't automatically mean it's dangerous. What truly matters is, what kind of atom is it? What type of radiation does it emit? How much energy does it carry? And how does it affect the human body? That's the real question. In the next video, we'll finally talk about radiation units. This is actually the reason I started making these videos. Units are standardized numbers, but they're one of the most misunderstood parts of radiation science. Once you understand which unit to use in which situation, you'll be able to read radiation data more clearly and free yourself from vague and unnecessary fear. This has been No More Misunderstandings. See you in the next video.